we're going to be taking you through a journey of identifying malicious traffic found amongst normal computer network activity. By the end of this presentation, we can hope that you can see the utility of applying some of the techniques we learned in this course to this type of highly technical, relatively dirty data. Our objective is nothing short than appropriately classifying malicious botnet traffic using a range of techniques both learned here in this class, as well as techniques that we had to acquire outside of the course. We're going to be running the full range of instance-based algorithms, to clustering algorithms, to ensemble algorithms, and to finally decision tree. Once these classification methods are done, we're also going to be looking at dimension reduction techniques, as well as active learning. Finally, as a bonus, we're going to be applying 3 of our most successful classification techniques to a new NetFlow dataset. Just as a background, we got this data from the Czech Technical University. In 2011, they generate network packet capture, or PCAP, in order to show how malicious botnet traffic, a type of malware, appears when present in otherwise normal benign network traffic. Network traffic are literally those bits and bytes that move between your computer and other devices hosting services you use, such as websites or file shares. This data set, known as CTU13, was posted online, and we are using an abbreviated version of that PCAP known as NetFlow data to conduct this analysis. And this is what NetFlow data physically looks like. It starts with a date that the material was captured, and then moves on to the duration, or the amount of time in which the connection occurs. Then it specifies the protocol, or the actual classification used for relaying datagrams across network boundaries. Most of the time, we're going to be talking about TCP or UDP, which are the most prevalent protocols in networks. These are the protocols that are actually physically carrying your services, your websites, your videos. However, we're also going to have to look at things such as Internet Control Messaging Protocol, or ICMP, and Address Resolution Protocol, or ARP. These are usually used to run or troubleshoot network traffic. Then we're going to be talking about source and destination IP addresses and ports. These are literally the logical locations and services from which and to you request and receive internet traffic. Next, we're going to be talking about flags. These are indicators of the type of action executed in transmission. So each protocol uses different sets of flags to say what it's doing, which made for a very interesting discovery process. Then we're going to be talking about the type of service. In this context, that means the priority given to transmission. Following that, we're going to be talking about the number of packets in the transmission, as well as the number of flows or packet groups required to complete the transmission. And finally, we're going to be talking about labels. Before now, we were all talking about dependent variables, at least in the original NetFlow data set. Now we're going to be talking about the response variables. We're going to be talking about whether or not a particular transmission is background traffic or traffic not from an infected host, legitimate traffic, or benign traffic from an infected host, or botnet traffic. This is malicious traffic. Now, I should note here that there was a separate class of botnet traffic called botnet filter legitimate. There are 2 classes of botnet traffic. The documentation was a little bit unclear as to the exact nature of this traffic, but this traffic appears to be what's called command and control traffic, or channels used to tell the botnet what to do. As such, we include it with the botnet traffic. And with that, Mukla will go into the cleaning process.
The very first process in our project was to clean the dataset, because initially our dataset had about 1.2 million rows, and this took almost 1.2 gigabytes of memory in our computers. So we figured this would be impossible to run the models on. So in the cleaning process, we removed all the missing values and non-alphanumeric characters, and then we encoded all the categorical features, and then we had to downsample the dataset to balance the labels, because in the original dataset, about 90% of the rows were either background or legitimate. So this might cause some skewing or imbalance in the models in future. So we downsample them to 2 categories, and the size of the dataset is reduced to 43,000 rows and 8 columns. Now we move on to the 5 important questions in our project. The goal of the first question is to determine if there are any variables that can be extracted from the IP address that is useful in our models. Using the GeoIP2 package, we were able to get the source location, that is the source country and the source city, from the IP addresses. And if you look at the graph on the right, you can see the majority of these botnet packets originate from Prague. But this could be mainly because our dataset is from Prague. So apart from Prague, there are about 70 other cities all over the world where these botnet packets originate. This can be clearly seen on this map, which was created using Power BI. The red bubbles indicate the origination location, and the red lines indicate their destination. And we can see that most of the sources are from Central Europe, and the destination are concentrated over USA, Europe, India, and East Asia. Now, handing over to John for second question.
So in question 2, we asked whether or not we could effectively expand the variable list by splitting some of the variables and meaningfully extracting values from them. First, we looked at flags. Those are the actions that protocols are taking during the transmission. We determined that no, while TCP flags, or one of the main protocols that's actually moving data, can be split, they lose context when considered individually. Also, as you can see from the image on the slide, there are 10 other protocols besides TCP in the CTU13 dataset. These flags for the other protocols could not be split. As such, we determined to keep all the flags whole and one hot code them later. Next, we looked at flow start. This is when the actual traffic flow or the transmission begins. And no, while we determined that we could find traffic spikes associated with botnet traffic, these instances were not regular or repeatable. So the minute or second values within the flow start variable could not be broken apart and analyzed one by one to help classification. So we kept flow start as a whole. Finally, we looked at the source and destination IP addresses. So because in question 1, we already looked at GeoIP2, the geolocation of each of the transmissions of the sources and destinations were already accounted for. So looking at the individual octaves, we could not qualitatively say that further information could be derived from looking at those individual octaves, since each of these IP addresses is tied to a geographic location already. So in North America, IANA is the authority for assigning IPv4 addresses in the North American continent. So since GeoIP2 already took that location information, we determined that no, breaking up the source or destination IPs by their octaves was not effective. And Mukula is going to be talking about starting to talk about the classification algorithms next.
The third question in our project is to apply various machine learning models on our dataset and see which one among them effectively classifies the botnet traffic. So the models that we're using are PCA, random forest, KNN, SVM, naive Bayes, bagging classifiers, hierarchical clustering, Gini decision tree, k-means clustering, XGBoost, and dbScan, all of which we study in Dr. Song's class. And before we move into any of our models, it is very important to note that our data set is heavily skewed because of the location variables. And this is clearly seen using the feature scores that we obtain. And you can see on the graph that the source city and source country have significantly higher scores or feature importance than the rest of the variables. And this could be a problem in our models. This might cause the accuracy scores to go up or down. So we decided to do it both ways. One, using all the variables, and the second way is to remove the location variables and see how it affects our model. Now, going into our first model, that is the random forest. So just to brush up on the topic, random forest creates decision trees on randomly selected data samples, gets the prediction from each tree, and then selects the best solution by means of voting. So when we apply this random forest to our data set, we can see that it gives us 100% accuracy. Now, this could be an error, because if you look at the graph on the right, you can see how the accuracy score suddenly jumps to 100% once we include the source city variable. So after removing the location variables, we can see the overall accuracy score is only 83.7%. So we believe in this case, it is better to remove the location variables. Now the next model is KNN. KNN represents a supervised classification algorithm that will classify new data according to the K number or the closest data points. The accuracy score for this is 96.9% when we include all the variables, and when we remove the location variables, it seems to go down a little bit, but not very much, about 83.2%. And the main thing to take away from this KNN is we applied a bunch of different K values to see which one gives the best performance, and um, looks like K equal to 180 gives us the best accuracy scores for our data set regardless of the location columns. So next model will be explained by Stephen.
The first method that I used was k-means clustering. This is a clustering algorithm which starts with a number k of randomly placed centroids. For each point in the dataset, one of those centroids is assigned to it, and that point becomes part of that centroid's cluster. The centroids are then located to the mean of these clusters after all of them have been assigned, and these two processes repeat until the centroids no longer move. So you can look at the confusion matrix and see that all but one of the entries were put into one of the two clusters used. So a k value of 2, which is what we're using for all the other methods, does not suitably cluster the data into any meaningful groups. I could have chosen either of these two as of the two clusters as true or false, because k-means clustering is an unsupervised learning method. So it does not output with any labels. The second method that I used was density-based spatial clustering of algorithms with noise, also known as dbScan. This is another clustering algorithm which can create a number of clusters of at least k points. These are considered clustered together if these k points are a certain distance from each other. This produced slightly more meaningful results than k-means clustering, but one of the groups still dominated the other, and they were categorized on largely a different trend than whether or not it was part of a botnet. The third method that I used was the bootstrapped aggregator, or bagging classifier. A bagging classifier fits several base classifiers using the decision tree as scikit-learn's default. And words. The last method that I tried was the bootstrapped aggregator, or bagging classifier. A bagging classifier fits several base classifiers. Scikit-learn uses the decision tree by default, and then aggregates the results of those base classifiers. So whatever classification is the majority for a certain data point is given as that final label. This produced very good results. This was the second best method of all the methods that we used behind the decision tree. Next, Emma is going to talk about the 3 methods that she used on this data set.
Hi guys, here we're talking about the hierarchical cluster we apply to our data set. So hierarchical cluster is most variable need the ON square memory. Because of this, most implementation will be filled at around 60,000 instances. So we need to downsize the data since our data set is too large. Here we only take 2% of our data set, about 9,000 variables. So there's 2 types of hierarchical cluster. One is top to down, another one is bottom to up. Here we are using the bottom up method. And first we get the data scaled and use the dendrogram linkage and to get a cluster graph. As we can see on the left graph, there's 2 hierarchical cluster. For the cluster 1, it can be categorized about 100% of the legitimate data. For cluster 2, but it isn't performing well. And also on the right hand side is the plural graph, which produced by the R. We can easily see from the color that based on the another factor and the label themselves. And so this is sometimes really useful to label, to get a label and features in each cluster. Next, we're going to talking about a decision tree we apply to our data set. Decision tree is methods construction a model of decision based on the actual value of this distribute in the data, and decision tree also train on data for classification and regression problems. As we can see, even after we move the location, the decision tree model still perform really high accuracy, and this is why decision tree is a big favors in machine learning model and is often fast and accuracy. And next, we're talking about a Naive-based classifier we apply to our data set. So Naive-based classifier is an algorithm that uses the Bayes theorem to classify the object, and it's popular to use in the spam filters. As we can see, after we remove the locations, our accuracy even get higher. This model indicates that the strong and independence between the attributions of our data points.
Up next, we have gradient boosting, which is an ensemble algorithm that attempts to turn weak learners into strong learners. It's very similar to AdaBoost, but instead of compensating the coefficients, gradient boosting focuses on the loss function or the error and compensates there. We chose to implement gradient boosting using a third-party XGBoost library because, according to tests that we cite in the paper, it is approximately 100 times faster than the default gradient boosting classifier with scikit-learn. And as you can see here, it achieves very impressive accuracy scores. When all variables are included, it's almost 100%. And when the location variables are removed, it still achieves a very respectable 86, 87%. Now, this tells us that adding weight to the loss function appears to be just as effective as adding weight to the coefficients, at least for this particular data set. Moving on to support vector machines, they're an instant-based algorithm that attempts to separate variables along the widest possible width. This is known as large margin classification. Now, here we also have to choose a special library. We chose the new SVC, or support vector classification library, because the default or the standard method with scikit-learn, SVC, can only handle into the low tens of thousands in terms of observations. Even with our downsized data set, we have 43,000 observations. So we were afraid that SVC might return erroneous results. Hence, we chose new SVC. And as you can see here, the accuracy scores are comparable to what we saw before. We see almost a 97% accuracy score when all the variables are included. It somewhat suffers compared to what we saw gradient boosting at 78, 79%, but that's still in the same ballpark of not being random. And this tells us with SVM that at least one type of instance-based variable has very significant success, both when country and city variables are present, as well as when they're not present. And finally, we're going to be talking about principal component analysis, or PCA. The idea here is to reduce the dimensionality of a data set, hopefully compensating for any potential overfitting, and also just making the data set itself easier to work with. Here you can see very flat results. So whether the variables are included or not, or the location variables are included or not included, we see a return of 82 to 83%. This tells us that when paired with a min-max scaler, it gives similar performance across the board. So we can be assured that this is a very firm result, that there's very little chance of overfitting. And next, Stephen will be concluding question 3 with a summary.
So here we have the results of all the methods that we used. The middle column shows the accuracy scores with all the variables included. And for most of these methods, these resulted in very high scores, and random forest had 100% accuracy. The methods that didn't perform well include the 3 clustering methods and the naive Bayesian classifier, which all scored between 50 and 60%. The right column shows the accuracy scores with the source city and source country removed. And for the methods that did well with all the variables, they still did fairly well, but not as well. Bagging and the Gini decision tree both scored above 90%. Gradient boosting, principal component analysis, k-nearest neighbors, random forest all scored above 80%, and support vector machine scored a little bit under 80%. The scores for The scores for k-means clustering and hierarchical clustering didn't change, and the scores for DB-scan and the naive Bayesian classifier improved slightly.
Analysis will apply to our data set. Dominant analysis is aimed to identify variables, otherwise known as the predictor, that has the most importance in determining the final classification of an observations in multiple regressions. So each predictor receives their relative importance by comparing their R-squared weights to the R-squared weights of other variables across all the subset modulus. This dominant analysis is third-party library provide to be the best platform to explore the dominant analysis, as it provides the efficiency at conducting the dominant analysis calculations, and it was stable and also provide a useful graph, as we can see on the next slide. So here's the dominant analysis. One of the track that dominant analysis library produced, and with the all variable from the clean data set, the city location of Prague and the country location of Czechia represent the Czech Republic. Together contain approximately 76% of the relative importance of all variables. While this analysis has a R-squared value of 98.26%, indicate that the model explains a very large amount of the variables present, and the two highest variable efficiency present the same information. As such, we want to remove them and to see what will be occurred. So this is the graph after we remove the Prague and Czechia variable, and we can see a more evenly distribute of the relative importance through a variable between SYN, which represent flag, and port 25 SMTP and port 35 DNS, still count for the disproportional amount of relative importance. But these are the technical variables that help to better get an attribute of the data streams, and we can focus on the harmful malicious activity. Sadly, this model only achieve R-squared value of about 41%. But we still provide basically to begin botnet search, and John will follow me to discuss.
In question 5, we discuss active learning, which is a semi-supervised learning method by which to conduct classification using iteratively increasing portions of a data set. The objective of active learning is to achieve accuracy rates that are commensurate with the larger data set, or at least that achieves some predetermined rate. In our case, we're starting with 0.5 percentage point of the original data set, so 215 observations out of the larger downsampled 43,000 observations that we have, and we're iterating 6 times over until we reach 1% of the downsampled data set, or 430 observations. In this chart, you can see our results when we apply the active learning or the random forest classifier. Here, even though active learning doesn't outperform random sampling, we still achieve respectable accuracy rates between 73 and 76% given the portion of the data set we're looking at. This improves with support vector machines, where we're seeing between an 85 and 86.5% accuracy rate using active learning. This marginally does better than random sampling by a few percentage points. And finally, when we look at KNN, we see similar results, albeit slightly worse. In this particular case, KNN paired with active learning achieves almost an 80% accuracy rate and is 1 to 2 percentage points higher than a random sampling. And in this chart, you can see the results with active learning that SVM performs best, followed by KNN and then random forest. And here we show very concretely how active learning influences the effects of each of these classifiers. You can see that it boosts the results of KNN by 1 to 2 percentage points. It has a marginal effect on SVM by between 0 and 0.5 percentage point, and actually has a negative effect on random forest, dipping it down to as low as 4%, or a 4% decrease in the effects of the random forest classifier alone. And with that, I will be followed by Stephen with the bonus.
Put gradient boosting here. All right. After seeing how much the source city and source country affected the results of our first data set, we wanted to try some of our methods on another data set that might not have the same patterns. So we took another CTU13 packet capture data set, and after cleaning it, we used bagging, the Genie decision tree, and gradient boosting on it. The results were comparable to the first data set with the source city and source country removed, although slightly better in the case of bagging and gradient boosting. And when we removed the source city and source country variables for this, and when we removed the source city and source country variables, all the methods improved slightly. You suspect that for this data set, the main component in determining whether or not a packet is part of a botnet might be packet size. And finally, John will give us a summary.
In summary, we discovered that there was a wide swath of algorithms that were effective at classifying a CTU13 dataset, specifically instance-based, ensemble, decision tree, and bagging. We also discovered some weakness in clustering algorithms and naive Bayes with this dataset, which we believe to be a result of the distribution of it. We also found through feature engineering and dominance analysis that there were a few location points that had extremely high relative importance to the rest of the data set. However, when we removed those data points, even though we did receive slightly worse accuracy scores as a result, we did find some technical indicators that did also have high relative importance that could be more universally applied. We also learned that active learning can be effective at boosting certain algorithms in their overall accuracy scores with relatively few data points between 215 and 430. Finally, we discovered through the bonus question that another portion of the CTU13 dataset could be effectively classified with the techniques we employed. And with that, we would be happy to take your questions on Slack.